Hello ladies and gentlemen, thanks for tuning back here today. Today I'm going to focus on the remaining test that I didn't cover in the previous lecture, and that's the Wilcoxon matched pairs signed ranks test. So today in lecture 9 we went over a variety of different tests. So we covered those with independent samples where you have two samples, and we covered parametric versions, so the two sample difference of means, the two sample difference of proportions, and then we also covered a non-parametric test using the Wilcoxon rank sum W. Then we moved on to the dependent match pairs samples, and previously I covered the t-test, so the student t-test for the matched pairs, but what I didn't cover in the previous session was the non-parametric test for the Wilcoxon matched pairs signed ranks test, and that's what I'm going to be covering today in this short video. So the question is, well, what if the data that I have don't conform to the assumptions that allow me to use the matched pairs t-test? So that could be that the data are ordinal, that the sample sizes are too small for you to reliably use parametric approaches, or potentially that the data are drawn from non-normally distributed populations. So I think it's important for me just to identify before I continue. The reason why I recorded two separate videos is because I think I've found a mistake in the book. So I've actually contacted the authors now to find if they can clarify this position, but I just wanted to raise it with you. So on page 170, when you look in the book at the breakout box for the Wilcoxon matched pairs signed ranks test, it actually says as one of the assumptions and requirements that the population is normally distributed. And I think that this is an error in the book. It contradicts the text, and it contradicts, all existing knowledge that I have of this test. So I've reached out to the authors, and hopefully they'll be able to clarify this query. But I just wanted to draw your attention to it before we progressed, in case there was any kind of confusion with you between what I've taught you in this lecture and what's written already in the book. Okay. So the Wilcoxon signed rank test essentially is the non-parametric equivalent for the student t-test. So what does it mean? Well, we use the matched pair differences ranked from lowest to highest. So let me just work through this summary, and then I'll give you an example of how we do this. What we do is we take the absolute difference between the two variables to determine the rank. So this is the difference between the first sample point. Say you sampled weather data from cornfields in 1974, and then you resampled the average temperature for 1994. Essentially, we're taking the absolute difference between those values if this is the right test to use for those data. When the difference between those two values is 0, so when essentially there's no difference, we basically just ignore these items in the ranking because there was no change. But then when the differences are tied for a particular rank, the mean rank is allocated to the pair. Okay, so this is how we actually carry out this method. I'm going to give you an example of the math that we use to calculate the test statistic, and then we're going to look at a version which I've hacked together in an Excel spreadsheet, and then hopefully that will provide you with some understanding as to how to run this test. So over here I've got the equation that we need to use. It looks really scary, I know, but it's actually very simple once we input the sample size and we determine which t value we need to use, and then that produces basically this ZW test statistic. So essentially what we're trying to do here is compare matched pairs for differences when you've got data that don't conform to the parametric based procedure. And the issue is that we need to obtain this TP and TN value. So this is the T, it's the sum values which are positive for the rank, and the sum values which are negative for the rank, and I'll show you how we do that in a bit. But the problem is that you need to decide which one to use, which is correct. Okay, so if your hypothesis is one-tailed, then you need to use the t with the smallest number of differences, so the smallest t basically. Whereas if you use the hypothesis which is two-tailed, you need to use the smaller of TP or TN, so the positives and negatives. I'm going to show you now how we calculate each of those. don't be daunted. This isn't actually as scary as this equation looks. A lot of it, as you can see, is just inputting the sample size, and you just need to know how to calculate that appropriately. So this is the example that I've taken out of the book, McGrew et al. And essentially what I've done is I've just copy and pasted the data here from an Excel spreadsheet where I've hacked out all of the numbers, and we've got the change in the ranks, and that allows us to get the key statistics of interest, which are down here. So it's the mean for X, so for this column here, the mean for Y, so for this column here, and then we're able to get Tn and Tp, so it's the sum of the ranks for the negatives or the positives. So let me break that down, okay? So for the example that we're actually producing here, you can look at the table itself on page 172, which is here. So this is for an initiative which attempted to reduce the amount of water that households are going to be using. Obviously, water has an environmental impact. Just processing it uses energy, it creates emissions. So as a consequence, we want to reduce the amount of water that is wasted. So this is a huge area of study. Within GGS at GMU, there are faculty members who work explicitly on water problems. So it is an interesting area to get into if you're interested. So essentially what we have are 11 households here who at the end of the survey period were still involved in the assessment and actually had data which we could use. So this is the amount of data, so the amount of water that was used before the implementation. So this is the number of gallons. So let me just input this here. I hope that that's clearer for you now. So we have the number of gallons that each household was using before the intervention, and then we have the number of gallons that each household is using after the intervention. And essentially what we want to do is we want to get the change. So we are subtracting, here we go, we're subtracting the x values from the y values, and that produces the change. So here it's minus 27.5, minus 10.5 on the second household, minus 4.9 on the third household. Okay, and then what we do is we basically go in and we allocate a rank to them from the lowest. Okay, so we end up having this ranking. And then what we need to do is we need to get the mean for x. So the x bar is here. So what we're doing is we are summing all of the data variables, the data points that we collected prior to the intervention for x. And then we're dividing by the number of data points that we have. Okay, so we end up with 152.8 gallons. And then after the intervention, we do the same. We get 146.5 gallons of water. Okay, and if you enter this text that I've placed here, and if you enter it with an equals in front of it, then you'll be able to, if you put it in here for the cell, it'll be able to recreate that particular number for you. And this is just saying sum all of the data points in B12 to B23, which is this, and then it's basically saying divide it by the number of values that we have. So it's just using the count function, and that's how we get this these numbers here. And they marry up with what's in the book if you want to look at the example, which is on page 172. And then it's a little bit more complicated for the Tn and the Tp values. Essentially what I do is I use a sum-if function. So what it's saying is sum any rank, so this red column here, if the change is, in this case, negative. Okay, so it's only summing those ranks where we've got a negative number in the change. And that contrasts with TP, where essentially we only sum the rank if the change is positive. Okay, so I hope that that's reasonably clear. You've got the data here, so you'll be able to play around with it and look at this, look at how it works out in the spreadsheet, and then also look at the example in the book. Once we've got those results, essentially, we end up with a TN value of 47 and a TP value of 19. We have 11 data samples in our data set. And say we have this question, okay, so, sorry, the question is actually wrong. What the question should be is, does a water reduction campaign reduce water consumption? Okay, so the point is that it's a statement where we expect water consumption in these households to decrease. Okay, so we've taken the amount of water that they each use at the beginning of the assessment period, and then we've gone back a year later and we've, after carrying out a water information campaign with them to help them understand how to reduce water, we've measured how much water they use. And therefore we expect that there's going to be a decrease in the amount of water consumed by these households. We don't have enough data for us to use a parametric test, so we need to use a Wilcoxon matched pairs signed rank test. We've got the values now from the previous calculations that I put together, so we've got the TN, the TP, and the number of data points. And then we're able to specify our hypothesis. So the null hypothesis is that there's no difference between the amount of water consumed before the assessment period and after the information campaign had been implemented. Whereas the alternative hypothesis is essentially that we would expect there to be a negative difference. So we expect water consumption over time as a result of this campaign that's been carried out to decrease. So we know that we're going to use TP here because we select the T which corresponds to the smallest number of hypothesized changes, and out of the two values, TP is smallest. So you remember we stated the rules down here for which one to use. So we want the one-tailed, use the T with the smallest number of differences. Okay. So how do we calculate the test statistics? Well, we need to input our data now into the equation which I gave you previously. So we want to get ZW, which means that we need to use the right T statistic, which hit with the T value, which here is 19, so for TP. And then what we need to do is we need to input the sample size, so the sample size is 11, and then we need to run that all the way through this particular example, okay? And then what we get as a result, the ZW value is minus 1.245, okay? So essentially when we get the critical value for this, we get a p-value of 0.1066, which is one-sided, which basically means that we don't have enough evidence to reject the null hypothesis. Really, we'd be looking at the 95% significance level for us to have a p-value that's below 0.05. We don't have that here, so we don't have enough evidence to reject the null hypothesis. So this suggests that the water reduction campaign didn't have a significant impact on reducing water consumption at the 95% confidence level. So I hope that that is reasonably clear for you. I've given you the formulae for how I calculated that in the Excel spreadsheet. I am going to show you now how we're going to do this within the lab environment using RStudio, so hopefully that's going to provide you with another way to understand this. If you've got any further questions or hesitations about this, please reach out, and when I hear back from the authors of the book, I hope I'll be able to provide you with a definitive answer on the error which I identified earlier to you. Okay, thank you very much for tuning in, and I'll see you all soon. Goodbye.